Okay, so continuing on with 16.2, we have one more practice question, writing full equations for a proton transfer type reaction. So hydrogen sulfite, HSO3 negative, is amphoteric because it's a good example of one of those protonated anions of a polyprotic acid. Write an equation for the reaction with water in which it acts as an acid and which it acts as a base. So if I take HSO3 negative plus H2O, if it's acting as an acid, that means it's donating its proton. So it's weak, so we're going to put the equilibrium symbol in the middle. Of course, it will make H3O plus, and then what will be left is SO3 2 minus. Same thing, HSO3 negative plus H2O, but this time it's acting as the base. So it's going to take a hydrogen from water. So the water will be OH minus, will be what's left, and this will be H2SO3. So now just identifying the conjugate acid-base pairs. So here we said HSO3 negative was acting as the acid, so this is the acid. This must be the base. Remember, the acid becomes the conjugate base. So this guy is the conjugate base, conjugate acid. And then you check that by looking at the reverse reaction. Does the conjugate acid act as an acid in the reverse reaction? And it does. HSO3 negative here is the base, and water is the acid. Remember, the base becomes the conjugate acid. So this is the conjugate acid, and this is the conjugate base. And then look at the reverse reaction. Does the conjugate acid act as an acid? Does it donate a proton? And it does. The next idea is this relative strength of acids and bases. And we will go into this in much more details when we start looking at Ka and Kb, when we're actually, looking at to what extent is the acid actually dissociated. Right now we just have weak and strong, but then we're going to go and actually look at numerically what makes one acid weaker than another acid. But here you can see that they're listed, that there's some strong acids up top and then weak acids down here. So they will give a hydrogen, but they will not dissociate completely. Bases over here are our strong bases. The ones that are weak bases will accept a hydrogen, but they will, once they take it, they're not going to necessarily give it away. You can also see that if you are a strong acid, right, this would be your conjugate base. And what we will notice is that the stronger the acid, the weaker the conjugate base. So we're talking about how much will you take a hydrogen ion, right? And Cl minus we know does not accept the hydrogen ion. It doesn't form a covalent bond at all. It's listed as negligibly basic. Whereas the strong bases, and these are things that you're like, what? CH3 negative? Yeah, we have never seen that before. But if you had the CH3 negative ion in water, it would grab a hydrogen and hold on to it. So in every acid-base reaction, so you can look at how this is an equilibrium reaction. We always say that if it's an equilibrium in the middle, so we would have, an acid reaction one way and an acid reaction another way. So which way is it favored? You could we're going to look in the future, and you could look at Ka and Kb values for this. But another way to think about is that the proton gets transferred to the stronger base. So if you look at this question here, it says, predict whether the equilibrium lies to the left or lies to the right. So when we first went over this, you didn't know what that meant. So we would want to say, well, which one is the stronger base? So first of all, let's identify the bases, right? The bases are the hydrogen ion acceptor. So the forward reaction, CO3 2 minus, accepts the hydrogen ion. And in the reverse reaction, SO4 2 minus accepts the hydrogen. So which one is a stronger base? Well, here's CO3, and here's SO4. And so if we look at these, it looks like CO3 2 minus is the stronger base. So if that is the stronger base, that means that the proton will get transferred to the stronger base. So this reaction, the forward-facing reaction, will happen more. So now that we know about equilibrium constants, what can we say about the equilibrium constant for this reaction? Well, if the forward reaction is favored, that means it'll be mostly products at equilibrium, which means K will be greater than 1. And then we'll continue on with 16.3, the auto-ionization of water. And this is really the basis for pH. So in any water solution, just like a glass of water, this equilibrium reaction is taking place. It's not taking place very much, but it is taking place so that you have a little bit of OH minus and you have a little bit of H plus, like this reaction is going on. In pure water, right, these two would be in the same amounts, and therefore the solution is neither acidic nor basic. Well, now that we know a little bit about acids and bases, you can go, well, we can write a K for this equilibrium reaction. Products of reactants, coefficients become exponents. So what are the products in this? Well, H3O plus and OH minus, right, over the reactants, but the reactants are liquid, so we don't use any reactants there. And so this is a formula that we can use. And this is a number, just like equilibrium constants that we could look at for Kc and Kp. We can look at the equilibrium constant for this reaction. And at 25 degrees Celsius, and that is important, it is 1.00 times 10 to negative 14. At other temperatures, that number changes, which means the pH of a neutral acid solution in like your body, which is a different temperature. So this reaction has a different kW, so it's different. So when you are involved in like biological systems, you have to account for that. When we look at this now, we go, okay, well, this is great because this can help me anytime I know the H plus, I can immediately find the OH minus. So an acidic solution is one where the H plus is greater than the OH minus. And we can always figure out what are the actual concentrations because the two of them have to multiply together to give you that number. So it kind of makes sense that as one goes up, the other's going to go down, right? They sort of play off each other. And of course, a neutral solution is when you have equal amounts of both, right? And so if these were both equal, you can see kind of where we're going with that. So here's a couple sample calculations of really just using that formula there. A solution in which the OH minus is 0.010 molarity, calculate the H plus. So anytime that we have one and we need to find the other, we're using this formula. 1.00 times 10 to the negative 14 equals the concentration of H3O plus or H plus, right? Those are interchangeable, times the concentration of OH minus. So write the formula, plug in what you know, and then solve. 1.00 times 10 to negative 14 equals, we know the concentration, I'll change that to H plus, since that's what it says, 0.010 molarity, right? Divide that out, we get that the concentration of H plus is equal to 1.0 times 10 to negative 12 molarity, right? The concentration of the OH minus is pretty high. Therefore, the concentration of the H plus is extremely low. This is the other way around, a solution in which, oh no, both of these, we have to find the H plus. So 1.00 times 10 to the negative 14 equals the concentration of the H plus times the concentration of the OH minus. The concentration of the OH minus in this case is 1.8 times 10 to the negative 9. So it's significantly lower than it was before. What is the H plus concentration equal? 5.6 times 10 to the negative 6 molarity. So now look at who is bigger, like which one is bigger. Here's the concentration of the OH minus. Here's the concentration of the H plus. Which one is bigger? The OH minus. So this first solution would be basic. And the second example, which one is bigger? The concentration of the OH minus or the concentration of the H plus? And that can get tricky because we're dealing with negative exponents in scientific notation. So don't mess that up. But this number is actually the larger number. So this is an acidic solution. Now, generally, when we look at acidic solutions versus basic solutions, what we're looking at is their pH, not just these concentrations. And that's what 16.4 is all about, that pH scale.